Hi. So today in this new episode, we're gonna try to implement the multi-layer perceptual, okay, which is very fundamental but very powerful neural networks. Okay, so that's essentially the most basic neural network, right? So to begin with, okay, so let's try to see how we're gonna use PyTorch to implement this. Okay, good. So we should import the torch and also an. Okay, so this will be the a optimizer, right? So this is the stochastic gradient descent, and then we're gonna use a MNIST 10-digit numbers to be our data set. Okay, so which is pretty easy to understand. Okay, so and that comes from this torch vision.datasets. Okay, and then we're gonna also need some data loader. So this data loader, that is just some function to help us to load those kind of data. Okay, so those data are already classified, right? So they have the X input and the label output, right? So those input there are some pixels, right? So there are just some numbers to indicate those pixels, and the labels are just the digits from 0 to 9, right? So the data loader, essentially it helps us to load all of those data to form a specific iterative formation. Okay, so it just simply construct those iterations to help us to try to feed those data in a for loop, right? So that's the data loader. That's it. Okay, and you can also try to use some TensorBoard, okay, which is basically something from TensorFlow, but you can use something else if you like, okay, to help to visualize the training and evaluating process. Okay, and the summary writer is just some writer for us to write those points that we need to visualize. Okay, those data points. Okay, good. So the first thing here, okay, so this is gonna be to see. So this is just some variable, okay, some global variable that we define to select which device we're gonna use. Okay, so this is just some variable that we say that this is the torch device, and we're gonna use this sort of CUDA if that is available, and we're gonna use CPU if that's not available. So that at least this guarantees us some device to use, right? If the GPU is not available. So if you want to use GPU, so first of all you have to have a GPU, right? And second, you need to install the GPU version of PyTorch, right, from the pip installation. And then so this is something we need. Okay, maybe you don't need this, but this will be pretty helpful to specify those two things, right? So something more important or necessary to have, and you see that there very shortly, is that we're gonna need to specify the GPU or the CUDA, okay, for the network that we define and for all the data in the for loops in the training and testing. Okay, so to use GPU. So this is a necessary step for us to do later. Okay, we'll see that. Good. So let's move on, and then we need to claim some global variables. Those are just some hyperparameters, right? So we say the batch size, that'll be just the size of each batch, right? So you're gonna how much data you want to put for each iteration of training, right? And we simply have something like this, or you can put maybe 512 or smaller. That depends on the specific situation, okay, that you are dealing with. Okay, so this can be changed, and those parameters are something important to revise when we after each training, right? So those are something also pretty useful. And we set this epoch, the number of epochs, to be 50, and learning rate to be 0.01. Okay, so this will be used in the SGD. Okay, so the next thing is to prepare the data. Okay, so we're gonna split, we're gonna load the training and test data from the data sets. Okay, and this is just some path of that. Okay, and then this we're gonna specify the train or to be true or false to have training or test data. Okay, and so let's put it smaller. Okay, if you can see this. So, and we're gonna say this, we're gonna transform this to some tensor, and also we're gonna download those. Okay, so that we don't need to download again. Okay, so the length of data, so we just take those length, okay, and we can see those later. So, and then this is the raw data, right? So the data they're just in some tensor format, but it's still not in our iteration format, right? Remember that we're gonna use the iterations to train, to form our main training loop, right? So to feed for the loop, we have to make those data in an iterative way, right? So that is why we need this data loader. Okay, so essentially this data loader is just an iterator, and that packs the data into those batch sizes. Okay, good. So, and then how do we do that? We simply put those data here, and we say the batch size is the number that we want to have, and then we can make the shuffle to be true. Okay, good. So next, we're gonna define the network. Okay, so the class net, so we know this previously, right? So this would be something inherited from module, and then we call this super init, and we're gonna keep all of those properties from the class from module, and then we're gonna simply define a sequential. Okay, so first we have to make this make this as a simple matrix, right? In two-dimensional, because so essentially we might have multi-dimensional, right? For the RGB of a picture, or maybe if even it's in grayscale, but we might have more dimensions, right? So here we simply need to flatten this tensor, okay, so that we can use the multi-layer perceptron. Okay, so and another reason is that we don't really need to keep the high dimensional way of those tensors, right? Because we're just using the MLP. We're not using like CNN or something else to capture the those features geometrically, right? Okay, so and then we're gonna have some linear. Okay, so this would be the dimension that we have, okay, from input. Okay, so normally we will have a bigger feature number in the top, or in the first sort of layer, and we can have smaller ones later, right? As we see here. So here we simply have 3 of those. Okay, and we need to match those dimensions, right? And this is something we already know from previous episode. Another thing very important to notice is that we also have those ReLUs, right? And we don't need any ReLU here after the last linear. This is because remember that the activation functions are just something for us to separate those linear or split those linear layers, so that those linear layers, they do not collapse to just one linear layer. Okay, if we don't have those ReLUs in between, then those linears, they just sort of we simply just multiply those together, right? So by the linear algebra, then and this will be simply just one linear layer altogether, right? And that doesn't make any so that doesn't have any non-linearity inside of this network, right? So that this function will be not very powerful to model this data, right? Okay, so that's this nonlinearity that we have for those activation functions, right? We don't need that for the last layer here. Okay, so since we have already put all of those here, so we don't need to write all of those in the forward. So we simply explicitly to specify this here. Okay, so that'll be just taking this model. Okay, good. So then we put this class to this net, okay, and we make this instance. And something important to notice, as we just mentioned in the beginning, we need to move the model to the GPU. Okay, so if you want to use GPU, normally GPU is faster. Okay, so for those matrix operations. So if you want to use GPU, then you have to specify this, okay, to the device that we just specified, either GPU or CPU, right? If we have GPU, then that'll be GPU. Okay, good. So and then we're gonna also load some function from the end to use this cross entropy loss. This is pretty standard. And then we use some also very standard optimizer called stochastic gradient descent. Okay, and that operates on those parameters and specify the linear rate. Okay, so and then we're gonna have those zeros to begin with the training step and testing steps, and also we will have this writer, okay, to be the sum writer for the tensor board. Okay, we don't actually need this for this pretty simple task, but we might need to visualize some for some big project, right? If data sets are pretty big, or if you need to. Okay, good. So for the training loop, okay, so let's begin with this. So for each epoch, I'm gonna print the number of epoch, and so this would be the training part. Okay, so the training part, so we're gonna first to train this. Okay, so this train will be just some function from the network. Okay, so and that simply that is saying that, okay, now the training starts. Okay, and then the next we're gonna write how to train this. Okay, so we're gonna so here we have those data prepared by the data loader in a iterative form, right? Remember that we need to use for loop to load the data, right? So here is the for loop. Okay, so and then we're gonna load this data. Okay, so for each item in this loop, in this for loop, okay, this iterative data, then we have those two, right? So we have already combined those together. So we have this, our x and y, and here that is something also important, right? So remember also something like this. Okay, we need to put our network to the GPU. So here we also need to put our data into the GPU. Okay, so those are two necessary things to do. You can put all of those to CPU, but or you can just put all of those to GPU, right? But if you put some of those to CPU and some of those to GPU, then there might be some problem. There might be error. Okay, so and then we put X to GPU and put Y to GPU as well. Okay, so the outputs. So later on, then all the other things will simply computed. They're computed in the GPU, right? So we don't need to have worry about those later. Okay, then the output. So this will be the Y that we compute from X using the net, right? And then we're gonna compute the loss by comparing those two Y's. So this will be the Y from the data set, and it will be the Y that we computed from the network. And then the optimizer, we're gonna initialize this. So we're gonna reset the gradients. Okay, so and we're gonna have this loss for the backpropagation, right? And then after we backpropagate our loss, then we can make a step for this optimizer, right? So we have this learning rate, and the optimizer simply try to update all of those, and that this makes one step, right, for the optimization problem. Okay, and then we count this training step to plus 1. If we take the mod for each 100 steps, then we're gonna print the loss and the current step. Okay, so and here we add an item. So this item is simply to convert the tensor to some value, okay, which is easier to see. And then we can also write those inside of tensor board, where we write this training loss, okay. And also remember to write the step, okay. So you're gonna need to record the loss for the corresponding step, okay. Good. So this will be the training, pretty straightforward. And then that is this training part. The next part, that will be the test. Okay, so you notice that this for loop aligns with this test, right? So the evaluation, the eval, this is simply just we just want to set this network to be this evaluation mode. Okay, so that means from here on, then we don't need to train the model. Okay, so we simply want to evaluate the model. So that's the meaning of this. This is pretty straightforward. And then we initialize the loss and the total. This will be not the number of accurate items, right? So this is not the accuracy rate yet. Okay, so and then with torch, there's no grad. So this no grad, again, that is simply some function to disable the calculations for the gradients. Okay, because we're testing the data here. We don't need any gradients for the test. Okay, again, this will be similar like the training loop. Okay, so for the data in the test data loader, and we have those data loaded, and again, we're gonna put all of those testing data to GPU. Okay, which is also faster and also consistent with the others, right? So because if you put your net on CPU and you put the data on GPU, then there will be some error, right? So they can't find each other. Okay, and then this is the output, and we compute the loss, and so this will be the loss, right, between those two. And then we simply add the total test loss. Okay, this is the value of the loss. And we don't need to backpropagate, right? It's because this is just the test. We just see how good we are doing, right? And then the accuracy, the amount of the accurate items, that'll be those items if we have the argmax of this of those outputs. Okay, so if that would be the same as targets, right? So essentially this means that if we have the correct prediction or the correct inference, then we're gonna count this as one accurate item, one accurate result, right? And we sum those across all the across one batch, right? And then we add those accurate items into this total accurate items. Okay, good. And then we can print all of those results, print the total accurate items, and the test data size, and the total test loss. Okay, and we can divide the total accurate items by the test data size. So this is essentially the total accuracy rate, right? And we can also print the total test loss. We can also write this into the tensor board, and we can also write this accuracy rate into the tensor board. Okay, and then I'm gonna +1 for the test step. Okay, and then we close the write. Okay, so this would be essentially everything for training a pretty simple neural network, a MLP, using the PyTorch. Okay, and on this MNIST data set. Okay, so here that'll be something I have already run from this code, and you can see that here that is up to here, right? And you can see that this accuracy, the testing accuracy, that still remains at 0.8. So that might because of this neural network structure that is still not good enough, or might because of those hyperparameters or something else, right? Or maybe even just because we didn't have enough epochs, right? So you can try to improve this result. And here we can see that all of those loss there in the training data sets, they're decreasing. So this is good. Okay, but maybe we just need more training loops to train this further, right? Okay, so and that'll be everything for this episode, and hope this will be useful for you to try to understand and try to implement some pretty fundamental neural networks in PyTorch. Okay, good.